Okay. Hello? How many people had some wine over lunch? I'm just estimating the fraction of people who may fall asleep. It's typically the people who did not have any wine who fall asleep, you understand. That's why I had some. Right. So I'm going to talk to you about chocolate, not for the first time, but perhaps for the last time. I'm going to talk about Conching chocolate. Autocorrect is a real pain, because half of a slice comes up as Conching chocolate, which would be, I guess, appropriate for the Olympic weeks. But anyway, so I'm going to talk about Conching chocolate. So this is Cargèse. I'm from Edinburgh. So as you know, chocolate is very popular. I don't know whether I should be surprised by this graph or not. But anyway, eating chocolate seemed to be a European thing. Right? I mean, this is the top, 15 or so countries, and most of them are European. And perhaps Switzerland shouldn't surprise you. But there are one or two surprises there. I mean, these are small countries. They must eat a lot of chocolate.
Is the definition of chocolate the same in all?
Yeah, all right. No, I know. I once had a French postdoc, before he came to Edinburgh, he emailed me and asked, can I buy food on the campus? I said to him, well, you can pay to ingest free energy, but whether a Frenchman will call it food is a matter of definition. So he agreed with me afterwards. Anyway, so, we've heard chocolate talks before, but perhaps no one has actually talked through where it comes from. So that's the cocoa bean on the tree. So when the cocoa bean first got imported to Europe in that long period between the 16th and 18th century, what people did was they ground up the dry cocoa beans to make a drinking chocolate powder. Can anyone see why that would be disgusting? It didn't stop it becoming very popular, so popular that the Pope had to decree that drinking chocolate does not break a fast. So everybody can actually drink chocolate on Friday and during Lent. But anyway, anyone can see why that would be disgusting? What's the composition of cocoa beans? Cocoa beans has got a lot of fat in it. So you try to have a ground up powder that is full of fat. The fat doesn't dissolve and make the drink very greasy. So if you try to grind up dry cocoa beans and make hot chocolate, take my word for it, it'd be disgusting. As I said, it didn't stop it becoming very popular, because if you can't have an alternative, then you just drink that. So everything changed. The first key step was made in the Netherlands by a Dutchman whose name I shall not try to pronounce. Any Dutch person here will tell me how to say all that? How do you say that? Like that. I hope that was recorded. Do you want to say it really loudly for the recording? Sorry? Say it really loudly into my microphone. I hope the recording heard it. Right. Fine. Well, right. So this guy discovered that if you just press cocoa butter, if you press the cocoa bit, dry press it, the cocoa beans, you can actually separate into the bit that makes this disgusting, the oily bit, the fatty bit, which comes out as cocoa butter, and the rest is a cocoa powder. And if you try to make a drink out of that, it's no longer greasy and disgusting, and it dissolves. So that became a craze. He obviously did not write a proper patent, because his patent soon ran out, and everybody did it. And in Britain, of course, it's made by Cadbury's. And there was no lawsuit, so I assume that this guy, whose name I can't pronounce, his patent ran out. So that was the state of affairs, and this was originally a waste product. I could not find what he did with, perhaps somewhere in the Netherlands there's an original cocoa butter mountain. That is, from this guy. Perhaps they use it to fill the sea and make powders and things. But anyway, I don't know what he did with it, but that was a waste product. He wanted the cocoa powder, drinking chocolate. So the next step, you have to move across the channel. There's the Joseph, Richard, and Francis Fry, three brothers. What they discover, if you take what this guy laboriously did and mix it back together again, technology never makes any sense to physicists. What do you want to do that for? You get nothing. But put some sugar in, then you mix all these ingredients thoroughly and pour into a mold, then hey, you get that stuff. You get chocolate as modern day. And then the final step, depends on whether you like milk chocolate or not, is good or bad step, is that this Swiss guy, Daniel Peters, in 1875, he discovered that if you put some milk powder in as well, then hey presto, you get that stuff, you get milk chocolate. Anyone know what the problem is? Anyone know why this is a cheating, these are cheating photographs, that the product that they made, that the Fry brothers and Peters made, is nothing like, still nothing like modern chocolate. What was the issue? You put it in your mouth and chew it, what are you likely to say? It's gritty. So there's a but. So it was gritty. It feels like coarse sandpaper. But if you don't have any choice, you put up with it, right? So the next step is a Swiss step. So it's Rudolf Lindt, as in the guy who makes Lindt chocolate famous. So you remember I had to put all those ingredients into mix, right? So he had a mixing machine. I'll show you what it looked like in a moment. Actually, I'll show it to you now. If you go into any Lindt chocolate shop in any self-respecting Swiss airport, including Zurich and Geneva, you go to the Lindt chocolate shop, but that's a photograph. That's not actually a spying guy. Scary eyes at the back. His machine looked a bit like there's a roller. It's a bit like these paint rollers, okay? Now, he was only supposed to mix his chocolate powdery and buttery ingredients for a few hours. According to Wikipedia, actually no, I didn't learn it from Wikipedia, I learned it from somewhere else, much less reputable. But anyway, according to whatever I learned it from, one weekend he forgot to turn his machine off. Happens, you know. So next Monday he went in, and it turns out if you actually mix this stuff for a very long time, like a weekend, it comes out and in the molten form like chocolat fondant, and when you've kind of it's totally smooth, and when you pour into a mold and it sets, it becomes what you and I would now think of as modern chocolate. So the disadvantage is it's not very sustainable and green because you need to put his grinding machine on for a much longer time, but he sells it for a lot more money. So in those days they were not thinking about sustainability, so that won. Now, I don't know about you, but I mean he called it conching because the word conch comes from this kind of seashell is called conch shell. Now, how many people think that looks like a conch shell? I know it's curved, right? But you might as well call my hand a conch. I mean, it's so I deduce that therefore Switzerland must be a landlocked country that they never see the sea, because so it took me ages to realize why he's called it conching, because he thinks that curved bit looks like a conch shell. Anyway, so the name stuck. So this is now called conching. So the process of a prolonged mixing, stroke grinding, stroke whatever, depends on who you read, what they think is going on. But that prolonged mixing process is called conching. And I'm going to tell you about the physics of that. Okay? So this is the stage of industrial chocolate making that consumers rarely know about, but you know about it really because if you paid attention to Paul Smith's lecture, he talked about conching, and he talked about what is conched. So the thing that you throw in, actually, at least for the mass chocolate producers anyway, not necessarily the artisan producers, and not necessarily the highest priced items, that's sold by Lindt, but most of them start with this disgusting looking powder, which is called crumb powder. So electron micrograph doesn't look very much better. It looks like sort of, if I don't put the scale on, it look like an asteroid of some sort. It does look like a bit like asteroids, right? But anyway, so we can go and find the pictures. I haven't put my slides on the Dropbox yet because I was still writing them last night, so you will get them when I finish correcting all the wrong bits after I finish lecturing. So each one of these is a sugar grain. The inside is a sugar grain. It's a sucrose crystal. And the outside is more or less coated with milk proteins and cocoa solids. So some manufacturers make their own crumb powder, and other manufacturers buy in crumb powder. So there are companies that supply crumb. Does Cargèse supply crumb powder, Paul? Where's Paul? This is when you discover which one of your friends is missing your lecture. Right. It's always worth asking questions like that because you find things out. Right. So anyway, so this is crumb powder. So I'm going to pretend that these are sugar crystals, but kind of rough sugar crystals. So I mean, conching is a large-scale process. Some of the machines can be the size of this room, but here's machine. You can tell this picture is made by a biologist because there's no scale bar on it. That was only half a joke. I mean, I absolutely hate those papers. They give you electron micrograph, and it just said magnify 4,000 times, as if that makes it all right. I mean, no, it doesn't. Anyway, so I mean, this can be, you know, me high or bigger. Okay, so in this particular machine, what you do is you put the crumb, that disgusting-looking stuff, plus some cocoa powder, cocoa butter, some cocoa solid. These are bits of the cocoa shell and other bits and pieces. This is what makes it brown, basically, in the end. And some lecithin. I'll tell you what lecithin is. You may already know is a mixture of phospholipids. You throw it in, and this is what the machine inside actually looked like in this particular version. What it has is these are two rollers that rotate on this axis, and this, on this shaft, the whole thing rotates this way. Can you see what it's doing? So there are two rollers that rotate next to a surface, or it's sitting on some surface on the bottom. And so these two little side rollers roll along this horizontal axis, and the whole unit rotates along the vertical axis. I think sometimes these two rotate in opposite directions too. But anyway, so you throw that stuff in, and then you leave it there for varying length of time, and what comes out is a flowable chocolate, amazingly. And typically, you don't even have to heat, because this process generates so much dissipates so much mechanical energy that the mechanical process itself is more than enough to melt the cocoa butter. So you don't even have to heat it. You may even have to cool it if your machine is rubbish. So I don't know whether anybody actually cools their machine, but you certainly don't need to put heat in. So the whole thing comes out as molten chocolate. So the key thing is not that Lindt discovered that you have to mix the stuff. You obviously have to mix the stuff. But what Lindt discovered, if you mix the stuff for a weekend, then it comes out really smooth. Okay, so so the question is, what's going on there? So you do mechanical action, temperature rises, melts the cocoa butter. It also, the high temperature also develops flavor and aroma. Thankfully, this is all chemistry. So when people ask me, I said, I know there are about 150 reactions collectively known as the Maillard reactions or Browning reactions. These are reactions between proteins and sugar and between the proteins, and the one common thing is it generates nice smelling molecules and generates brown color. I kid you not, there is the International Society of Maillard Reactions. When I retire, I'll go to one of their conferences. Perhaps there's a parallel session on each reaction. 150 parallel sessions. I mean, I just don't know what parallel session they've got, because there are about 150 reactions at least. So one day I will go to it and I'll tell you about it afterwards. But anyway, so you know, the brown, the color, the flavor, you know, all of that is chemistry. But the question I want to ask is, what is it doing in terms of physics? The bit that doesn't change anything chemically. Okay. So if you read the books, and there are quite a few well-known chocolate manufacturing textbooks, they will tell you one version or another of this sentence. Their picture is what you do. You do that sort of thing, is to spread butter on toast. And what they say, what it does is it spreads the cocoa butter on the sugar crystals. And if you ask them why, they say because cocoa butter does not wet sugar crystal. Now, if you want to disprove that, what's the simplest experiment you can think of doing? I mean, I'm a lazy person. I like simple experiments you can do in 5 seconds with no money. Right. So you know, you do the following, right? I mean, you because that statement isn't true. I mean, what we did, really did this. We just took a sugar crystal, because they're quite big. You can put them in a sugar bowl, use tweezers, magnifying glass, and you just drop some. I mean, we didn't use cocoa butter. We used some sunflower oil, but you know, it's a triaxyl glyceride, and it does this. I mean, there are 4 billion years of evolution behind that piece of apparatus. Why not use it? It's better than anything else you got in your lab. And you know, frankly, even in the UK, we pay those better more than we pay for computers. So you know, use it. It does this. I mean, it doesn't do lotus leaf. The contact angle is significantly less than 90 degrees. I mean, sometimes it's very easy to disprove all the textbooks. So we did it in about 5 minutes. I remember I was in Paul Chaikin's lab, and he said, let's go get tweezers, get some sugar, get some sunflower oil, magnifying glass. Magnifying glass took the longest to find. There's plenty of microscopes. I don't need a microscope. I just want to look. Right. So I can tell you the textbooks are wrong. Any textbook that tells you Conching spreads cocoa butter onto sugar is just wrong. So what is the physics of Conching? There you are. See, now I told you. I didn't put that in deliberately. I hate autocorrect. There you go. That's called real-time PowerPoint. I mustn't do that. I must use my gadget here. There you go. Right, so it's not true because you can do that experiment using the eyes, and so what's the physics of Conching? Okay, so that took 6 years. There are a variety of things to learn from this paper. The first thing you learn is never write the title of a paper by committee. The reason that title is that long is everybody want their word in there. And I was too weak to say, no, we're not doing it. I mean, that's the worst title of a paper I've ever done, because no one remembers it. I don't remember it. So never write titles by committee. That's the first thing you learn. Second thing is, quite often, especially for those of you doing PhDs, it takes a long time to define the right question. Typically, in a 3-year PhD, it takes about 2.5 years to define the question and a half year to do it. Because if you define the right question and having made all the mistakes, you can do it really fast. So the whole project eventually took about 6 years. It took us 3 years to define the right questions. We knew the textbooks were wrong at the beginning, but we didn't have the right question to ask. So what does it do? In other words, I don't have a good hypothesis to test. Once we had the hypothesis to test, it becomes relatively easy. That's an important lesson. You need to ask the right questions. Okay, so it was a collaboration with New York University and Paul Chaikin. So it's the most publicity-generating thing I've ever done so far. So we made it to the New York Times, so their science column is called Trilobites. It was very interesting because there's a statement down there, further down is actually wrong. So I asked Veronique. She said, I know it's wrong because it's a statement about lipids and she has a molecular biology PhD. I said, well, why don't you change it? She said, because it's too complicated to change it. Okay, so she won. But anyway, so there is one statement in there that is wrong, but you have to read further down, so that was all right. So we got into the New York Times. What else happened to us? Oh, we got into some trade journal. Some of you may read this thing. I even got onto the Scottish News. Let me just make the sound. How do I do the sound? That's not good. Never mind, just to prove that I got onto television. Never mind. That is not me. just, one points this out. That's not my hand. There you go, that is me. Anyway, I thought the commentary could be quite interesting because they really have a Scottish accent, unlike me, I don't. But the really interesting thing, so this is the conching process. So, we put, so I just want to show you this movie. So we put all the ingredients in. Where did we put the ingredients in? No, not that bit. So, we pour all the bits in. You notice the postdoc carefully did not allow me to touch the machine. Which is quite correct. So this is the end product. The most interesting bit about that was I nearly got myself sacked because, not because I was, badly dressed, but because the presenter, without telling me, she wanted to take a chocolate bar out to eat in my lab. And then I pointed out to her, you will see in a moment, she was about to actually eat a chocolate bar being filmed in my lab in front of that notice and shown on prime time Scottish television. Because I would definitely have been sacked. But anyway, that's not me either. Right. Okay. Look, I've got to say this because, look, chocolate research is very glamorous, but we do need to know that there is a dark side to this. Okay, I just have one slide. I just want to point out to you that there are ethical issues to do with food research, not just chocolate. And I think, if we do this sort of thing again, maybe we should have a few ethics talks because, chocolate does involve a lot of child labor and all the rest of it is not just because a charity says so. U.S. Department of Government, the International Labor Lab, or whatever it's called, Labor Bureau, International Labor Affairs, also admits it. That is an interesting book to read if you're interested in this kind of subjects. So I just have a footnote to say that we ought to think about these things in today's climate. Right, so we published this paper. And if you had listened to the commentary, or indeed if you had seen some of the other headlines, what I said was, what we discover here is not just useful for chocolate, but in fact is in any industrial process where I want to take some powder and a small amount of liquid as possible, and to end up with a highly flowable, high solid volume fraction suspension. Industries call that by different names. Some call it incorporation, some call it mixing. But anyway, so for example, if you happen to be dealing with a powder that explodes, I don't mean just a powder because the powders explode, but actually a powder of explosives. Then what you don't want to do is to transport a powder. You want to actually mix it into a suspension to transport it, but you want it as low cost as possible, so you want to make a high volume fraction suspension of your powder to transport. The people in Sandia National Labs actually have to deal with that because they make explosives and they grind them down into powders. So, there are lots of industries. The cement is another. So, here's a high performance concrete. But it started off as a powder. You want to make a high performance concrete. You want it as high volume fraction of solids as possible, but you want it to be able to flow. You want to extrude something like a catalytic converter for your car. The real thing is more square, but this is a research picture from the Fraunhofer Institute in Germany somewhere. And so if you want to extrude this, you want to take titanium dioxide, aluminum dioxide powder, you might want to mix a little bit of liquid in, and you want to make it into a complex fluid that has a yield stress, but nevertheless flowable. You want to extrude it through an extruder. So there are lots of industry in which you actually do need to maximize phi, maximize the solid volume fraction, without compromising the final flowability. And in chocolate, you want to maximize the final phi because at the moment, consumers think that fat is worse for you than sugar. So you want to lower the fat. One way is to put more sugar in. I don't know what we can do if consumers think it's the other way, but at the moment, if you want to maximize fat, the easiest way to put more sugar in, for example. But anyway, so the maximum phi, in the case of chocolate, as I said, you can label it as low-fat chocolate. What you just don't tell anybody is this is high-sugar chocolate. Because unless, of course, you make chocolate with air in it, which is another solution. So in these cases, you want to maximize phi because the higher solid content translates into high mechanical strength. Okay, so there are all kinds of reasons why you might want to make a suspension with as little liquid as possible, but you want it to be flowable. Okay. So the question is how much solids can you pack into a suspension that can still flow? So everybody knows that if you plot the viscosity of a suspension against, or normalize it by the solvent viscosity, the graph looks like this, and it diverges. You can fit it to anything you like. So that is some sort of Krieger-Dougherty model. I started counting, but I gave up. I started counting how many ways the word model has been used in this summer school, and I'm only here for 1 week. You need to work out, the word model can mean a mouse for biologists. It can mean an equation purely for fitting without physics content, or you can mean something that you actually make a physical model, balls and springs, and then you write the equations down for that thing. But by the way, if you do interdisciplinary work, you really have to work out what you mean by a model and what the people you're talking to mean by a model. So if you call this a Krieger-Dougherty model or Bingham model, whatever it is, it's purely an equation with practically no physics content in it. The only thing they're supposed to tell you is that it diverges at some point. It stops flowing. The only number that has any meaning that you might want to attach to is this. I don't even want to argue about this. It's even wrong for the Einstein limit. But never mind. It diverges. Whatever your favorite equation is, it diverges. At some point, it stops flowing. Okay? So the question really is, what's the physics of phi j, and can you do anything about it if you're an engineer? So this is about the physics and engineering of phi j. So the colloids 101 answer, in other words, if you take the first course on colloids, whether it's in physics or chem-eng or physical chemistry, the colloids 101 answer is random close packing. This is taking spheres and putting them in at random. And I mean, this number was obtained, for those of you who think you're doing a boring PhD, spare thought for John Finney, who was J.D. Burnell's large PhD student. Burnell thought the way he can get that number is get a lot of ball bearings, guarantee monodisperse, throw it into a balloon, cheap, few thousand, pour in ink, also cheap, and some glue, and when you glue the spheres together, when it's set, you rip off the balloon, you pull the spheres apart. If two spheres are contacting, the ink trace on there would be a circle with a blank bit in the middle. So poor John Finney has to do that with 3,000 ball bearings, 3,000 times. He started doing computer simulations at that point and said, I'm not doing it again. There's this computer next door, which is the size of this room, that chucks away with vacuum tubes, and he started doing computer simulations. But anyway, so that number was originally obtained by Burnell literally by counting ball bearings and ink blotches and how they can't contact. That was possibly the cheapest public-funded experimental results in terms of pounds per impact, in terms of science ever done in Britain, because that is important about liquid packing. So that answer, which is based on the geometry of spheres in 3D, the answer is about 0.64. No one really knows how to calculate it yet. Every few years there's a rumor that someone knows, but usually dies without trace. So this is entirely, but whatever the number is entirely determined by geometry. So if you tell me you're doing spheres and you're in 3 dimensions, then the answer is, in principle, determined. And it's about 64%. It's the densest you can pack without putting crystalline order in. Okay? So if you know how to do that, write it up, you'll be very famous. But the number is about 64%. But the point is, there's no physics in here. This is mathematics. It's entirely determined by geometry. By the way, people know how to calculate these sort of numbers in 24 dimensions. It turns out to be much easier. 3 dimensions is a pain, because each one has about 10 neighbors, and 10 is embarrassingly big, but not big enough. If you're in 24 dimensions, you have so many neighbors, you really can do averages. Mean field theories work. Now, in 1D is easy. What's the answer in 1D? 2. Everybody can do that. Someone has not been drinking wine, or someone has been drinking wine, maybe. But anyway, so in 2D is also relatively easy, but actually, I don't know what I didn't calculate for 2 and 3D. But 2 and 3D are maximally difficult. But the point is, this is geometry. There's no physics in here. So that's a colloid 101 answer. By the way, if anyone ever want to estimate this number for a polydispersed distribution, you should read this paper by Far and Good. Is it in Dutch? Is it approximately close? I just realized that if my throat hurts, I'm doing the G right. So it's Far and Good. Right. What is that word beginning with G in Dutch that is incredibly useful, which means it's illegal but no one cares? There is such a word. Gedogen or something. It's approximately that. That's the best Dutch word to learn, by the way. If a Dutch policeman stops you, you just say that word and say, yeah, all right. I learned it, I genuinely did learn that in the context of, I'm sorry to say, but peeing in a canal in Amsterdam. Not that I was doing it, but someone told me that that's one of those categories. I said, such as what? And they said, you pee in a canal is strictly illegal, but no one cares. Right, okay. Where was I? Oh yes, this is a fantastic paper. You want to estimate for your distribution what the maximum close packing is. It really works, and Rob is perfectly happy to send you his code. Okay, so what that means, and by the way, this is important. So I'm now talking about a high shear viscosity. So if you beat the hell out of this, and you ask where it diverges, then it says it diverges random close packing for hard spheres. And that is found to be true for colloidal suspensions. If you do 100 nanometer silica, you measure the high shear viscosity, that is not good. Yeah, but how did that happen? Russian sabotage. Right. Okay. Nowadays you blame everything on that. Right. So 64% for hard spheres. Fine. So that's phi RCP. Okay, so you have to stay really awake during this lecture because I need you to read subscripts. So that was the colloid 101 answer. The colloid 201 answer, George Peter gave it to you. So if you take that colloidal suspension, but rather than beat the hell out of it, don't beat it at all. Just let it be. And then if you want to measure its viscosity, only very gently touch it. Measure the low shear limit viscosity. Then you will find that, in fact, that low shear viscosity diverges at 58%. That's coming from Edinburgh, we call it the summer tourist limit. In other words, you get to the point when there's so many tourists on the main street that you can't escape the cage of tourists around you to break out of the cage. It happens in other cities too. It happens in Amsterdam too. But in Amsterdam, at least they can fall into the canal. But in Edinburgh, there's no canals. So there really is a hard limit. So that's the point. Long before you reach random close packing, dynamically, the thing is arrested. That's called colloidal glass. Who remember George Peter telling you about that? Only one. You should make them all pay the fee. Twice. No, come on. You remember that, right? Did George tell you about that? Fine. They're just not admitting it. You're behaving like undergraduates. Sorry? You are behaving like undergraduates. Right, okay. We once said an exam question in our final year physics, and a student came up to us and said, part A is not fair, that was school physics. Well, yes, physics is a cumulative subject. I mean, it's just as good as saying, I don't know how to add 1 + 1 = 2 because that was school mathematics. I don't know, just go away. And that's not good. Right. Right. So this is determined by crowding. The particles cage each other. And so the system divides a finite U stress at 0 shear rate. You need to shear it at a finite stress before it flows. So George told you about that. So that means that if you look at the... Actually, do I have another slide on this? No. Okay, so I have to... So in other words, if you now plot that graph, I thought I had the graph, but I took it out. If you now plot that graph, should be eta 0. The 0 shear viscosity now diverges at 58%. I thought I had a slide with that graph, but I took it out for some reason. Okay, so for the Brownian suspension, if you shear it really fast, you can get as far as 64%. If you at the low shear limit, the thing gets stuck in a glass at 58%. Okay, so that's colloid 101, colloid 201. So now I want to talk about non-Brownian suspensions, because chocolate has bits in it that are 20 microns big. So diffusion coefficient of a sphere is that. You can define a time that it takes to diffuse its own diameter. That is basically polystyrene in water. It isn't, but it has the same radius and 1 micron, the viscosity is about water. If you stare at it, it takes about a second to diffuse its own size. Random direction, but it displaces its own size. So you can define a Brownian time. This thing goes as R cubed. So a sphere twice that size takes nearly 10 times longer to move a second. So what that says, if you fill an evacuated space shuttle with ping pong balls, that is not a Brownian suspension. I mean, in principle, it could be a suspension, but if you evacuate it, there's a little gas in it anyway, but the particles are so big in any case that it will take forever for a ping pong ball to diffuse its own diameter. Okay, so basically anything bigger than, I don't know, do I say it here? Anything bigger than sort of 5 microns, I mean, it's not as big as 10, but one is just about Brownian. You can see it. You don't get bored looking for it down a microscope. Okay, so anything that is 10 microns is certainly non-Brownian. So what about those systems? Okay, so it turns out that non-Brownian suspensions are nasty. Why do I say they're nasty? Look, here's one reason why they're nasty. If you take sticky particles of this kind, you shake it up, you go to coffee, you come back, you can make a gel. Because they move, they stick to each other, and the clusters move, and they stick to each other, right? But for Brownian particles, if you fill the space shuttle with ping pong balls covered in double-sided sticky tape, it does not gel. They don't move. They will never find each other, right? You have to do something to kick them into gelling. So the point about non-Brownian suspensions is like elephants, only worse. It remembers everything you've ever done to it. In principle, a Brownian suspension encodes its entire previous shear and other histories in it. You can't read it, which makes it worse, but it encodes the whole lot. It knows everything you've ever done to it, because the only way anything is going to happen to it if some external force or object does something to it. It doesn't do it by itself. That's why Brownian suspension nasty. Those who have worked on it knows that you have to be very careful how you load your rheometer with these suspensions, because it remembers how you loaded it. If you don't load it the same way as the previous person, you don't get the same answer. So for non-Brownian suspensions, again, I'm now back to infinity. This is the high shear viscosity. The question is, where does it diverge? Again, that is important. And it turns out that, summarizing a lot of simulations and experiments, that number is 54% or thereabout. You can argue whether it's 53 or 56, but it's not as high as 58. It's not as high as the colloidal glass transition. In any way, for this graph, for the glass transition, that is 8 is 0. Embarrassingly, because that includes myself, some of us has published papers on colloidal glasses using spheres that are almost non-Brownian, and in fact, I think we are probing this physics, not the other physics. There are many papers in literature, including one or two of my own, where actually we're not probing colloidal glass physics, we're actually probing this physics, which is mildly embarrassing, but never mind. Right, so that is known as phi m. It took me a long time to realize why the original people who did this use m, because it clearly is not maximum, because maximum is 64%. So it turns out m is an English substitute for the Greek mu. Mu as in friction coefficient, as in this is frictional, and friction will play a big role. So that's the mystery for m. So where do we see that number? The answer is we see that number in granular packing. So if you take dry grains, so the question is, and did they get any granular lectures the first week? So here's beginning granular lecture. So you would ask, on average, how many contacts per sphere do I need on average? Not when you count each individual one, but on average, how many contacts Z do I require minimally for the pile to be mechanically stable? The answer is, if they are frictionless, the answer is 6. James Clerk Maxwell first did that kind of argument. You can write down a number of equations, a number of constraints, and when you match the two, you find that you need 6 neighbors to provide normal forces, because it's just purely frictional to make it good. But if the spheres are frictional, if they're highly frictional, I'll tell you how highly in a moment, then the answer is 4. And so at that point, when there's a minimum number of contacts is there for mechanical stability, that packing is called isostatic packing. So if it's 6, if it's frictionless, then the number for dry grains is that number, is random close packing, 64%. But the reason why this is relevant for us is that it turns out that the dry grains people have always known, and they sometimes call it random loose packing. Some people don't think this is random loose packing, but I'm going to use it because I like it. The Oxford Dictionary does not disagree. So anyway, if there's frictional, they only need 4 contacts to be stable, then you don't need as many particles to make 4 contacts on average, and that number drops to about 54%. And that's the number we saw before. So it turns out that somehow dry granular suspension physics reappear in wet suspensions. I'll tell you why in a moment. So what this means, as I said, this number is got by counting number of constraints and the number of equations that you write down from mechanical, so you write down Newton's law, net zero force is 0, that net force is 0, and you write a number of constraints, and then you have to match the 2. Then the point about friction is, so if you don't have friction, 2 spheres next to each other, if they're infinitely hard, that gets rid of this constraint. They can't go into each other, okay? But you're still left with 5. 2 degrees of constraint, 2 degrees of freedom are sliding, 2 degrees of rolling, 1 degree of twisting. So it turns out if you remove the 2 degrees of sliding freedom, then that number drops down to 0.54. So how frictional is frictional? I can't remember. I'm sorry, I couldn't find it quickly last night. This is somebody's simulation. It could be Sibbett, but I find it and put it in. But people have done this in 3 dimensions. If you ask in a granular packing what the number of the average number of contacts is, then at friction coefficient of less than 10 to the minus 3 is 6, and it does this. So in other words, it's quite sharp. The thing happens round about 0.1. Okay, so if you're 0.01, it's definitely, you can think about it as non-frictional, but by the time you get to 0.1 or above, it's basically frictional. So it's a reasonable myth to say, if you give me your friction coefficient, if you give me the order of magnitude of your friction coefficient, I can tell you roughly where you are. And of course, the interesting stuff happens here. Okay? Is all this making sense, by the way? Who's asleep? I mean, those who laugh at that certainly was not asleep, right? So at least a few people are not asleep. Right. Something should have happened. What happened? Because I asked it to change. Oh, there you go. So that bit to the left of the yellow bit, I will more or less say frictionless, but around about 0.1, I would say they're frictional. So I would replace the truth by a step function. It is not terrible. Yes. Yeah, that is static. It's absolutely not dynamic. Every time I say mu, I mean static. Thank you for that question. When I say friction, from now on, I mean static friction. The bit that is even less understood than dynamic friction. This is frighteningly complicated. Yes. So the question is, why is this number that is relevant for dry granular packings reappear in non-Brownian wet suspensions? So here's a story where I took the journey from being labeled a heretic to being a mainstream sort of person. Yes, Adam. I don't know, who's the friction expert? Enrisha. At least you came, right? I mean, so. No, there's no, I'm glad you said that. I was going to say that, but I wasn't going to say it because I wasn't an expert. But there's no physical reason why you shouldn't be. You know, what's the friction force is bigger than a normal force. I mean, there's no known law of physics that says you can't have it. I mean, that's what I thought, but yeah. That's the best we can do. So the fact that you can have frictional contacts in a suspension used to be heresy. And it was used to be heresy because of this. So this is the best book on suspension dynamics that I know has been written by Gazzelli and Morris, by Thibaut Gazzelli and Jeff Morris. One of the best things about the book is all the diagrams are hand-drawn. By the way, if you ever want to write a book, do that, because they also hand-drew all the graphs that they took from paper, so they don't need to ask for permission from the publishers. That's very clever. They got an artist to actually hand-draw the graph accurately. Redraw the graph, and you just redrawn from, and you don't need permission. But the other diagrams, actually, I mean, these fabulous diagrams. I mean, I had two copies of the book, one for the physics and one for the diagram. I was sent one for reviewing. Okay, right. But they sent it to me after I bought it, which is very annoying. Anyway, so when you try to squeeze two spheres together, the same approach to shear flow, but it turns out if you do the mathematics, it takes forever to squeeze the last bit of liquid out as that gap gets smaller and smaller. So the squeezing force diverges as the gap to the -1. For shear is slightly better, it diverges a logarithm of it, but in either case, the lubrication force, whether it's in squeeze flow or in shear flow, diverges, which means that two spheres will take forever to squeeze a liquid film out and touch. Ergo, there's a theorem. The spheres don't touch. So I decided to at least learn, one word in many languages. I don't know what I cover everything, but there's always a but. Okay. I know about 4 of those. Okay, so the but here is this. Smooth particles only occur in mathematics, right? So real particles are rough. So in fact, people should have known this latest by this paper. I think there are hints of it before, but I mean, this paper from Helen Wilson and her collaborators shows, I mean, this is a proper fluid dynamics paper. It has equations and tensors from about halfway down page 1. This is a proper mathematics paper. It has a theorem. They prove that if the surface roughness is more than about 0.1% of the radius, the lubrication film breaks and they touch. That isn't much. If you do 100 nanometer silica, it isn't much. I haven't got the foggiest idea after even reading that paper many times, so I don't think they try to solve that. But this is a purely hydrodynamic problem that they solve. In fact, in practice, what they solve is when does the lubrication film break? Not quite when they touch, but they certainly assume that when the lubrication film is no longer there, they can touch. Well, if you can think of a way of writing that paper, but in 3 lines using scaling arguments, I would love to have it. I mean, I would love to have it to get an argument why that sort of number. But at the moment, the best paper I can find that actually has that number but appears believable is that. Right. So, I keep asking the German speakers in my audience to help me with this. What I want is one of these German words that are about this long. That means, I don't care whether you call it friction, but whatever it is, you should constrain mutual sliding of the 2 particles. But I mean, that must be possible to have a German word this size to say that. It sounds really learned, right? I mean, so anyway, yes, is the answer. Whatever it is, but that insight came a little bit later after we convinced ourselves that old-fashioned actually touching will do it. But after all, 2-gear wheels certainly can't slide, but you wouldn't dream of calling that friction. But it's whatever it is that stops the 2 particles sliding past each other. Okay? So yes, whatever that stops sliding is the minimum length English hyphenated word that whatever it is that stops sliding. It's good for PRL because it counts as 1 word when they do word count. You can always hyphenate and tie PRL and say this is 1 word. See what they do. That would be my last paper to submit. 1 word PRL. Right, it's great. Right, where was I? Oh yes, so it turns out that things can break. And so Jeff Morris and collaborators did quite an early simulation in 2014 where they simulated a suspension and showed that if there's no friction, this thing diverges at 0.64. Okay? And then they progressively increase their friction coefficient. So for every friction coefficient along here, in principle, you get a different curve. So it turns out that these curves shift to the left. So by the time you get to mu j, I mean, I should ask Jeff for the 0.1 curve. The 0.1 curve is somewhere around here, about in the middle. But everything happens between 0 and 1, basically, as here. Okay? So if you make the friction coefficient infinitely large, then that divergence happened at, in their case, 0.56, but they use a slightly different polydispersity than me. I sometimes get it at 0.54 in experiments, but never mind. Is lower, whatever it is lower than the colloidal glass transition. This is the infinite shear viscosity. This is the high shear viscosity. Okay, I'm going to stop there. Have I lost anyone completely yet? Must try harder. No? You still with me? Is that all good? Because this is after lunch. This is known as the death slot, because you're all supposed to be falling asleep. So I must check that you are not dead. Right. So, now you now pay attention here, because this is a key thought. What it turns out that for real particles, when you increase the applied stress, you can drive this transition. So for example, let's remember to hold this horizontally, because otherwise it shows too little. There you go. So for example, okay. So it turns out that for particles, I'll tell you what the color means in a moment. At low stress, they're lubricated. At high stress, they become touching and frictional. So for example, if this represents hairs in sterically stabilized particles, then there is a stress beyond which the hairs can be driven into interpenetration, or they even collapse. If it's a charge stabilized DLVO potential, then hopefully you either know, you've been told that usually it's a maximum, but if you apply high enough stress, you can go over that maximum, and they can touch. Okay, so whatever, for any way that you tend to stabilize your particles, there exists a stress, which I'm going to call sigma star, but other super and subscripts are widely used. I'm going to call it the onset stress. There's a stress beyond which you essentially ping all your contacts from lubricated to frictional. Again, it's not sharp, but I'm going to pretend that it is sharp. There's a critical stress beyond which at least that starts happening. So now you have a suspension that is at constant phi. You start off with low friction coefficient, the viscosity is here. As the friction coefficient increases, you go up from curve to curve. Okay, you get what I mean? I could put all that down in algebra, but I thought not after lunch. Okay, so as I increase the friction coefficient, as I increase the stress, the viscosity goes up. That's the phenomenon of shear thickening. And that's what essentially allowed you to do the stun of running on cornstarch. Okay? So at high stress, they are in frictional contact and the viscosity goes up. You got that? How long have I got? When did we start? Oh, we started at 2 o'clock, not, yes. Not 1 o'clock. I just briefly thought we started at 1 o'clock and I have 10 minutes left. Then I'm lost. Yes, that's a very good point, but the change, yes, that is a good point. You could take that into account, but it only changes the numbers but not the physics. I mean, yes, if you want real accuracy to the second decimal place to account for everything. But usually I'm working on yucky bits of chocolate crumb where I'm lucky to get the one figure. So that, no. Because that tends to be a few nanometers in a 20 micron particle. So yes, if you can do it if you want, but yeah, so yes, but no is the answer. Okay, you cope with some algebra or not? No calculus, I promise. Right, so what Wyatt and Case did, what Matthew Wyatt and Mike Case did was this. So I'm going to take the relative viscosity as diverging in some form, and they just took the simplest they can find. And the crucial thing is now the jamming volume fraction is stress dependent. And they say in my suspension, the fraction F of the contacts are frictional, and the fraction therefore 1 minus F is non-frictional. When they take the simplest ansatz, that's my most useful German word, the whatever it is, that Dutch word is more useful than the Dutch word. Ansatz means I'm just going to write it down, don't ask, because it's useful and it works. Right? So the units are right, but apart from that, bleh. Right, so this is an ansatz. It's the simplest ansatz they can do. If you really must, it's a linear interpolation. So they said if F is 0, no frictional contact, and they jam at random close packing. If friction contact, all of them are frictional, this is 1, this goes away, and it's phi m. I mean, you can't go simpler than that. I mean, you can put all kinds of other things in it. You only make life more difficult, the physics doesn't change. Got it? So that just says the jamming volume fraction is stress dependent, and what the stress does is to drive the contacts from, to start with, F is 0, to end up with, at high stress, sigma F is 1. And so this is that curve. So they said the fraction of frictional contacts is a function of stress, and they non-dimensionalize it by this sigma star. Basically, the stress scale given by the stabilization, if you like. So if this F is go to 0, sigma is much less than sigma star, then F go to 0. If sigma is very much bigger than sigma star, then F goes to 1. So you can choose your favorite function. I mean, when we fit data, we use some sort of sigmoidal function, and there are too many fitting parameters, so we put down alpha equal to 1, but you can use any of your favorite function that has this property. So this is a phenomenological model. It gets the phenomena right, but don't really trust the detailed numbers. So basically what it predicts is that, I mean, this graph really should be turning 45 degrees and backwards, but never mind. So it says the system jams at 64% at low stress. And at some critical onset stress, it starts moving lower. And at very high stresses, it jams at this phi m. Understood the graph? Apologize if you're red, green, unable to read, but this is red, this is green. Gee, is that red or not? Yeah, never mind. Right. So, again, if you have, this is not supposed to interfere with my, right. Not good. Right. There you go. So if you have a fixed volume fraction suspension, if you increase the stress, then you're getting closer and closer to jamming. You get closer and closer to jamming, the viscosity goes up. So you are moving towards jamming to meet it, sir. Well, that's not what they did. They just said the fraction of frictional contact changes, but you can recast that in your favorite words. But they said the fraction of frictional contact changes. So in other words, they only have 2 friction coefficients, either less than that critical thing, or those friction coefficients they said is lubricated, all of those above, but if you really want to resolve all of that, I'm sure you can do a high level thing. But you're much better spending your effort doing a non-mutant field tensorial version, because I think that is just playing with, numbers. It doesn't add any new physics to it. But yes, you could do that. Right, so the viscosity goes up. So that's shear thickening. Right. So here's the schematic summary. It just says the viscosity goes up with the applied stress. So at low stress, the contacts are lubricated. None of them are frictional. All current contacts are mu much less than 0.1, so I'm going to say they're non-frictional. Up here, at high enough stresses, all current contacts are much less than 0.1. I'm going to call them all frictional, and so they are rough. The stress is enough to press them to frictional contacts. And so there, you need each particle, essentially contact 6. There, they essentially contact 4 for mechanical stability. Once they're mechanically stable, it jams. So the jamming volume fraction there is higher than here. That's the summary of the new understanding of frictional rheology. So let me just show you a whole lot of data to show that this is not just make-believe. So these are 4 micron size PMMA spheres stabilized at PHSA. HSA is what you spent this morning hearing about to make these fun oleogels. This is the polymer of it. So these are stabilized by hairs, and as you can see, at different volume fractions, the onset of shear thickening is about here, and the onset of shear thickening doesn't change the volume fraction. At exactly the same stress, the particles are pressed into frictional contacts. So these lines are fits to that wide case theory. You write all the algebra down, so that's the sigma star. So just to show you it works with yucky stuff, this is calcite, this is actually industrial calcite. I mean, the trouble is, you write to these people, you said you order a kilogram, they roll about laughing, so I'll give you free because the minimum order is a ton. So I have a kilo of this, I've used about a gram of it. But okay, anyone, if you want calcite, write to me, I'll give it to you, okay? So I love you because it takes up space in my lab. But I don't like throwing things away. Retirement's the only solution. Right, okay, so those are 4 micron calcite crystals. They're definitely not spheres. I mean, which is which, you know? Can fit wide case theory to it. Cornstarch, it really does cornstarch, it looks like that. Like asteroids. Monodispersed silica back to spheres. I mean, so the phenomenon is generic. So long as you're not dealing with long, thin needles, broadly speaking, you get a jamming volume fraction of mid 50%, something like that. You pretend they're spheres. So the only other thing I want to tell you about this, I go back to, I do remember this about chocolate. I will get back to chocolate. I want to show you that this works for calcite, and so for sugar crystals, I have excuse to do it. This onset stress turns out to be a strong function of the diameter of the particle. No one understands it, I'm not going to go through it. But broadly speaking, it goes down to something like -2, and PMMA is a very good -2 in silica. I think it was -1.6, but it's quite a strong power. That's not understood. I'm not going to go into it. It's not understood. But nevertheless, it's empirically true. Which means that by the time you get to, what is this, 10 to the 4 nanometers is 10 microns. I mean, 10 to the -1 pascals, it's just, when you look at it and it shear thickens. Never mind loading the rheometer, never mind throwing it down a pipe in a building site, right? So what I'm about to say is technically nonsense, but it actually does make sense. I need a Dutch word for that. Non-Brownian suspensions are always shear thickened. Because whatever you do to it, anytime you do anything to it, the stresses are bigger than that. You do anything to it, you're driving all the contacts into frictional, and they're in that shear thickened state, so you only pack to phi m. Does that make any sense? Of course, if you're just sitting there, actually, no, sitting there is under gravity. So sometimes even gravitational stress is enough to drive him into frictional contacts. So for all non-Brownian suspensions, in practice, it's quite hard to see. So this is the limit of my viscometer and the boredom of my students, and then basically this window moves this way. So for non-Brownian suspension, you only ever see this bit. It's permanently shear thickened. You cannot apply the sort of stresses and wait the sort of time that you need to do a non-shear thickened bit. I think if you, no, because if you do the diagonal approximation, it goes as ow. If you actually do the diagonal approximation for spheres, it goes as ow, not ow squared. That's the annoying thing. Yeah. We can discuss this later. I did check it before I make that statement. But I could be wrong, but Mike agrees.
I used it in my model, the diagonal approximation for like spheres.
Yes.
It goes at R, and that was an argument that went on for a year.
No, it does work out. I mean, it works out to be R. If you say you need a constant force to put to collapse the hairs, which seems reasonable, if you said it's a force, and you use the diagonal to work out how much you actually need to push it, it comes out as R. It's not just F over R squared. That's what I thought, but I stood corrected. Anyway, hang on a moment. Right, so this is when I begin to move back to chocolate. So basically, if all the contacts are non-frictional, is here. If all the contacts are frictional, is here. So when you increase the stress, it goes from there to there. You all got that picture. Okay, so at low stresses, the contacts are non-frictional. I increase the stress, they go to there. That immediately raises the question. What happens if at low stress, I'm there, and I increase the stress? The moral of this story is look before you leap, because there's nowhere to leap to. There ain't any branch on there. It's too late. So what happens? You start stirring a suspension. It starts off at zero stress. You start stirring it, and you're here. What happens next? There's nowhere to go. The answer, if you're doing it in a rheometer, which is basically confined by surface tension at edges and by your plates, then essentially, I'm not going to talk about it because just unspeakably horrible things happen in a rheometer. You could just about write a journal rheology paper on it if you start to speak about it, but you can read it and it's quite clever. But we ended up measuring the inertia of the rheometer plates. But anyway. But if you do in a rheometer, unspeakably horrible things. The first time we did chocolate, because chocolate is one of those, you'd basically fling all the powder out and coat my wall with chocolate. So that was okay, but I mean, that's also unspeakably horrible. But suppose you stir this. No. Show me a shear band up there, I will love you. I mean, I love you already anyway, but I love you more. Which sense are you using the word model? As in, someone wrote it down but never actually checked in the rheometer, or what? Yeah, but they're wrong. I mean, you don't see it. I mean, the fact is you don't see it. You put a suspension that is about 5 in the rheometer, you don't see shear banding. No, but Lees-Edwards boundary condition is not a rheometer. Let me say that again. Lees-Edwards boundary condition is not a rheometer. It hasn't got surfaces. No, when you don't see it. That's my problem with those models. Right? When you actually confine it between surfaces, it does not do that. It sometimes fractures. But that's what it is. But if you now do it unconfined, say in a food mixer, in other words, there are lots of free surfaces, it can do whatever it likes, just beat it up in open air, or just shake it rigorously, this happens. I need music to this. So this is 4 different times. Okay? So this is just put some powder into a bottle, you measure an amount of liquid, so that if it is homogeneously mixed, it will give you a phi that is about phi m of the system, which I have separately determined by doing the rheology and fitting the curve. Okay, so I know this is about phi m. Magically, they turn it all into little granules that are about the same size. A control pressure rheometer is not a rheometer, it's a very clever rheometer. I exclude everything that I said about that one. So yes, that one needs a separate lecture or on its own on controlled pressure rheology. Yes, I'm not familiar with that. I mean, I've read the papers, but that's not what I do. And it's not relevant for chocolate because that's not what the chocolate people do. No. I mean, it's extremely clever and it's very nice. I wish I had one. I want them to build me one, but I don't have one. But yes, thank you for raising that. You can do, so look up the papers from Marseille. They're very clever, but that's not what we do. Okay, so if you have lots of open surfaces and you shake it up, you shake a system up that on average will give you a phi that is above phi m, this is what happens. And that process is known as granulation. There's a biological process that happens inside cells. It is also called granulation. If you want to search for granulation, you have to get rid of that millions of papers first. It's very, very annoying. Typically, we put granulation and powder, you get it. But the first time I searched for granulation, I panicked because I read 5 Google pages and this phenomenon did not come up. I can't remember what it is in a living cell, but there's a process called granulation. Anyway, so if you shake or beat a powder with some liquid that on average is about phi m, this is what happens. It granulates. Why am I showing that again? Right. So the physics is as follows. You've all stood on wet sand, right? You might have even done wet sand on just out there. You stand on wet sand, it dries, right? And that's because wet sand is a suspension that is right at the edge of that phi m jamming. And so if you stand on it, it's basically at phi m, it can't flow. The sand has to flow. The particles get out of the way for you to let you stand on it. So in order for it to flow, it has to dilate. The particles have to poke out of the liquid surface because there's no more room. It's jammed already. So when the particles poke out to the liquid surface, it goes dry. You got it? That's what happens. So here's a cartoon explanation. It's almost proved by PowerPoint, but it's quite a nice one. It was first suggested by those guys, and we did some work to show that it's not complete cartoon. So this is assuming that you have lots of free surfaces for things like that to form. You're not confined into your little rheometer plate. You're beating up in a food mixer or something. So the particles have to dilate, have to poke out of liquid surfaces in order to flow. Okay, so you're beating it in, they have to deform, so they have to flow over each other. And so they poke out of surfaces, but you see here's a negatively curved capillary surface here. So it exerts an inward capillary pressure. So if that inward capillary pressure, gamma over r is the rate of the particle, gamma is the surface tension here. If that inward capillary pressure is bigger than your onset stress, it drives all of those particles into frictional contact. You're at the frictional jamming point, so it basically jams the system. It auto-jams. Does that make some sense? Not many people have progressed beyond that verbal description to describe this process, but we think that's more or less what happens. No one quite knows how he selects the overall size of this, but there you go. So broadly speaking, if you allow it to make free surfaces, it dilates, it pokes out because it's already at phi m. In order for it to deform, it has to poke out. The moment it pokes out and it becomes dry on the surface, negative capillary surfaces occur. The negative capillary pressure drives the thing in, and it maintains the above sigma star stress even after you stop beating. When you're beating it, you are applying the sigma bigger than sigma star, but when you stop beating it, the capillary pressure applies that stress and remains jammed. And those are the granules. Okay, so it's
How compact do the particles have to be? Sorry.
well, inside, if this picture is correct, then inside is exactly at phi m. Slightly below because someone's poked out, but 0.55 for spheres. And no more than that, if they're non-Brownian spheres. For Brownian spheres, or if your stresses are below, that's a good question. If you read this paper, it shows you that if you beat it up in your granulator with stresses that are substantially below sigma star, then the middle can be 0.64. The same physics applies. Yes, but only if you beat it very gently with anything, with any particles at any size. You have to kind of stir it at that sort of speed for this to happen. You stir it at any real speeds or any real stresses, the middle is 0.55, if it is spheres, okay? So this is important in pharmaceutical industry. They sell machines the size of this room to do granulation. This is just from any random number of websites. You can buy one of these granulators. They granulate things. But also, I mean, here's a random video from, so this is people granulating fertilizers in a farm somewhere in China. So they feed fertilizer, powder, and liquid in, and what comes out is these granules. Okay. So back to chocolate. Take the chocolate crumb. Okay, I think I have just enough time to finish the chocolate bit. Take chocolate crumb, which is this powder, as you see on the left-hand side. So I take that powder, I put some sunflower oil, only because I don't want to have to melt the cocoa butter or work in a hot lab. But the rheology turns out all the rheological phenomena are the same. This is just allow me to cheat a little bit. You take this lecithin, which is a mixture of lipids, you put it in granules. This is actually a picture of it. The first time I saw the postdoc do this, I said, you forgot to put the oil in. No, he hasn't. He just put the oil in. I mean, it looks completely dry, right? But trust me, there's, by volume, about 40% of oil in there. That's why I thought they'd forgotten to put the oil in. But no, they poured the oil in front of me next time, and it looks like that. After you stirred it just a tiny bit. And you keep stirring it. What does it do? Check that you're awake. It granulates, right? It granulates under your nose. Turns into granules.
For this you need good wettability, right?
Yes, I've just shown you my eyeball experiment, the oil dust wet the sugar.
And is there studies that look at the effect of wet?
There is an infinite, semi-infinitely large industrial granulation literature. That generates a lot of heat. But in terms of light, in terms of what is going on, I'm not totally convinced. But yes, I mean, you can find literature on practically anything, any aspect, for tuning anything about a particle, about a liquid, about the way you beat it, blah, blah, blah. But I just want to understand what's going on, so that's why I do the simplest case. Yes, yes, the literature is semi-infinite. Right, oh yes. So, what does it tell you? What it tells you is that I'm trying to flow this system, I'm trying to make things deform and flow at above phi m. Remember, in all these pictures, phi is fixed. I'm not adding any more oil. So here is above phi m, and yet when I keep beating it, eventually I end up with a suspension that can flow. Phi isn't changing. I start off above phi m. The only thing that can be going on is that phi m must be increasing. You got the picture. I know the moment I see it granulate, I know you're trying to flow the suspension at about phi m. The fact I end up with a suspension that can flow must mean that it's below phi m. The only thing that could be happening is phi m is changing. They can only be moving up to meet me and to go past my solid volume fraction. So, I mean, a long time ago, this is so long ago that the paper is in the Transaction of the Society of Rheology. This is before Journal of Rheology was Journal of Rheology. This is a long time ago. So what they did was, these guys took almost one of the dispersed silica spheres, I think they're glass, they call them glass spheres, and they progressively sinter them. So B is mostly trimers, D is beginning to get to about 10 mers, and those are unspeakably large, horrible aggregates. And basically, they measure the viscosity as a function of solid fraction, or volume fraction. And as you can see, I mean, they didn't fit it, but the place it diverged goes down. Okay, as the aggregate becomes more and more non-spherical and more horrible shapes, they pack less and less well. And so, of course, the frictional jamming point goes down. I mean, these are so, I can't remember how large they are. They're so large that they're undoubtedly frictional. Okay? So, I mean, it's not very deep. But if you actually replot the data and try to fit it, the jamming volume fraction really goes down when you go this way. Okay? So all that means is that, in fact, if I do conching, I'm going the other way. So it means that the crumb particles started off like that. As I beat it, I mean, it's embarrassingly simple. It starts off like that, so phi m is very low. As I beat it up, phi m goes up. So in other words, I mean, the movie is like this. So this is my mixture. Composition is fixed. The original phi m is here because they are horrible aggregates. And as I beat it up, phi m moves up, and eventually it goes past my composition, it becomes a flowable suspension. I mean, in the end, the answer was embarrassingly simple.
Looking at the glass beads getting aggregated, could you use such approach to model attractive suspension that also form this kind of?
Yes, but that needs 2 more lectures, which I haven't got time for. I will have one slide, but if you want to talk about it, we can talk about it later. But yes, it's a short answer, but the long one is about at least a lecture. I mean, I just given summer school last week in Udine. That took a whole lecture. So.
What about the whole process? Like, are you sharing or mixing or however you want to call it?
Can I come back to that? That's my final slide, which has not yet been written. That's when I'm going to say what remains to be thought through. If I know, I'll be writing the paper now. But yes, I think that's one of the best questions around. And I think shear is rubbish at doing it, which is why if you're doing a rheometer, it just flings the whole bloody lot out and, right. Shear, I know, from all kinds of experiences, is about as rubbish a way you can do it. Correct. So I think whatever is happening in the patented conches, whatever it is not shear. And if it is, they can save a lot of money by changing it to non-shear. But we didn't get to that bit, they stopped funding us. So. Which is why I can talk about it and speculate. So what we did here, this is a complicated graph. Wake up, this is a complicated graph. This is the complicated graph. Now what we did here is this. We take a mixture that is at this volume fraction, we beat it up, we conch it, and then we diluted the final mixture, and we get these points. We took a mixture at lower volume fraction, and we conch it, we dilute it, we get these points. What is obviously going on is to grind up the aggregates effectively. High volume fraction is better. It's beginning to answer your question. It's not what kind of stress, but you want to pack it as dense as possible because you're making them grind each other. Right? So the denser suspension grinds up better, and so they diverge at a lower volume, a high volume fraction than the one that I don't grind up as well. You get that? So if I put less in, basically I use it to mill each other. It doesn't work as well. I mean, that's almost trivial to say, but it's nice to see. Right. So here's some subtle stuff. So, I mean, you read our paper, I tell you how much lecithin I add in altogether. But it turns out I add it in 2 shots. I add 1/5 of the lecithin here. I do all this. Then I add the rest of it. So this is a phospholipid molecule. It has 2 tails. It has a charge head group. Most of them have charge head groups. So the reason why I need this is that if you break an aggregate apart, you need something to stabilize the fresh surfaces. Otherwise, they just stick together again. So you definitely need something to stabilize them, otherwise it's a pointless exercise. As soon as you stop eating it, they just all stick together back again. Okay, so you need a little bit. But it turns out if you put it all in, it doesn't work nearly as well. And we haven't proven this, but we think what goes on is that because you want to grind them, and again, beginning to answer Thibaut's question, you want to grind them, you want friction between them to put mechanical energy in. So if you reduce the, I think lecithin, I'll give you evidence for this later, lecithin reduces the static friction coefficient. So I don't think you grind them up nearly as well. And in fact, if you read a lot of recipes in the literature that adds in what they call the superplasticizer, they always tell you to add it in steps. Almost never add it in one go. They want to do this kind of thing, and I think that is why. So you do all this until it's just above 5 m. You notice it's still matte. The particles are still poking out. But there you add the rest of the lecithin. And you reduce the friction coefficient just a little bit more. It shifts 5 m just a little bit further on. This is shiny. Particles no longer poking out. The eye is a very good judge of when the thing is just above or just below 5 m. Just look under a bright light. Everybody else thinks you're very clever. You say, oh, it's just gone below 5 m. How do you know that? Well, I can see it. Right, so this is where you add the rest of the lecithin. Right, so there you go. So here's the evidence. So if you look at the high shear viscosity of that shiny chocolate, you stay at a single volume fraction, say here. If I lower the friction coefficient, the viscosity drops. The high shear viscosity. That's what happens. So the interesting thing here is what it tells you is that lecithin actually acts as a lubricant. It has a little minor job at the beginning to stabilize the surfaces, stop them sticking together. But is one of the major jobs, is actually lower the friction coefficient. And things that lower friction coefficients tend to be called lubricants, although I don't know whether it's the right word if I wanted static friction coefficient, but never mind. It is or it isn't the right word. The expert is shaking her head, which can either mean you're wrong or what. No one ever used that, but the word doesn't exist. I don't know what the word is. So again, again, I need a German word this long. That means that which reduces the static friction coefficient. So I'm going to call it lubricant, right? Yes. So there are all kinds of other things. But if you ask the metallurgy people, how do I make a good lubricant to make a bigger friction coefficient, they will tell you what the lubricant has to stick onto the surface. And this is the only time I ever read papers that have quantum mechanics in it. So these guys do very clever, proper quantum simulations and all the rest of it. You're not on this paper, right? You're just nodding your head. But anyway, you know these people? Yes. But they're good at it. So they did this simulation. And what they discover is that lecithin turns out to, I'm not going to go into the details, but it turns out that all the head group of lecithin has enough bits on it to make, how does it say? They make about 5 specific hydrogen bonds with the sucrose surface. And these all add up to some number that is hundreds of kTs of binding energy. So to rip that off, you need serious stress. So that's why lecithin turns out to be a good static friction modifier. I'm now going to address what happens when they're sticking. So this is your one slide. This hides in a 1-hour lecture in it. So if you take the final chocolate, you measure its rheology, it looks like this. It doesn't do the shear thickening stuff. I've so far assumed that I'm talking about a frictional system that does shear thickening, so I've been lying. All lecturing is an act of controlled lying. The question is when you omit it. Right. If you control it wrong, it's a bad lecture. Okay, so I'll leave you to judge. But anyway, so it looks like this. It doesn't do the shear thickening thing. So the reason for that is, in fact, the particles are sticky. So there is a finite yield stress. So the particles are sticky. Not surprising. The sugar is not refractory index matched to oil. But it turns out there is a different surfactant, and this is genuinely an unspeakably horrible molecule. Is Alexandru here? I mean, am I allowed to call this an unspeakably horrible molecule? It is polyglycerine polyricinoate. But then the whole family of them depends on what you hang off where, and I mean, it's just PGPR. Voila. Right. That's the sort of molecule that really scares physicists. Anyway, so American chocolate typically, cheap American chocolate adds this, even cheap European chocolate doesn't because it tastes waxy. But it turns out that what this does is it actually does what you think surfactants do, it lowers the yield stress. Until the yield stress becomes lower than the sigma star. So because the scale is so large, you can hardly see, but can you see actually, this actually does shear thicken. This is higher than here. So if I just show you this bit, this bit has a classic shear thickening shape. And that's because I lower the sticky yield stress down to below sigma star, I see the shear thickening. So this really is a frictional suspension. I mean, they all come basically to the same point. This is determined by the static friction coefficient, which lecithin lowers. I think that may just be what it happens to all kinds of other things. It happens to calcite when you stabilize it in PA, but I'm not going to talk about that. Why am I showing that again? Oh yeah, so can I go on for another 5 minutes? This is an important footnote. So it turns out that the chocolate people have been trying to say whether this is true or not for years, decades, maybe a century, by laser light diffraction. They want to see whether the particle size really is decreasing when they conch. They spend millions on machines, these big companies. I told them why they shouldn't, and I said, next time before you do that, give me half that money. I'll tell you don't spend it, and you save half the money. It's good for me, good for you, right? And it's just a fantastic deal. But they already spent it. I said, why don't you sell it on eBay, give me half it? Anyway, never mind. When Alphonse van Blaren's group did this, they make some of the best monodispersed spheres around, which means that they are also very good at making monodispersed dumbbells. They made a reaction, they make monodispersed dumbbells. Here is the small angle X-ray scattering data for their monodispersed dumbbells. Here's the theoretical prediction for a single monomer. The difference is in this bit. You calculate what that would be in laser light scattering for something like the sugar particles in a chocolate. All of this happens at below 0.5 degrees. You want to do 0.5 degree light scattering, can be done. Luca Cipoletti is very good at this, but you need a room. I mean, how long is Luca's original low-angle light scattering? I mean, the room is twice the size of this room or some ridiculous thing, isn't it? But you need a long room to get the low angles. And almost no one does it except Luca. Does it still have the machine? So if you want to do 0.5 degree light diffraction, go to see Luca in Montpellier. But it's a specialized hobby, right? So almost no one does it because the commercial instrument certainly does not scatter at 0.5 degrees. I'll tell you that because they are this size. Okay? So my answer is that you can never tell you're reducing the particle size by laser diffraction. Just don't even think of trying. Just give me half the money, I'll give you consultancy. So that's the way it is. So it turns out that by doing rheology, by actually doing this kind of stuff, that's bad news. So this process, the fact that this is happening and the particle sizes are reducing, you need that complex argument, and it took me an hour and a half to give you, via rheology and frictional suspensions, but almost for sure that this is happening. But don't ask for direct evidence. You will never find it, even in the electron microscopy. So there you go. That's the end of my lecture. I'm sorry to go over a little bit, eating into question time, but there it is.